All right, I think we're recording here, so we're going to go ahead and get started with Section 5.2, definite integrals. We're just going to run through a few things here quick today, and then you'll have a few problems to work on. I think that you're going to find that this assignment isn't too terribly awful. I think that you'll be able to handle it. It's building upon a lot that we've been talking about the last couple class sessions. And so we start with this wonderful stamp, big hair and all, of Leibniz, who came up with all this notation and this jazz in the first place. So that's where we're heading to start with, I guess. So with that, let's see if I can get my computer figured out. We're going to talk about Riemann sums today, which we have been talking about, whether you knew it or not. We're going to talk about definite integral and some notation there. We're going to talk about how to make integrals work on your calculator, and we're just going to kind of play with those things today, I guess. So here we go. First couple slides you just need to kind of watch, sit back and enjoy. You see the same parabola that we were looking at earlier. Hopefully you recognize that as a midpoint rectangular approximation method, MRAM. But all of those, LRAM, RRAM, MRAM that we've been talking about, they're all Riemann sums. Riemann was another guy that did a lot for calculus and the development of calculus. So he came up with being able to add up all these areas of rectangles to have a sum. So we see that the MRAM, and we can approximate that area under the curve using that. The width of each rectangle is called a subinterval. You might remember that from our program that we would run on our calculator. The entire interval there is called the partition. And thinking about what might make that approximation better, kind of be pondering that in the back of your head. That's something that we've talked about a little bit. The subintervals don't have to all be the same length. They can be different sizes so that we could, because we can find the area of each individual rectangle, and so they can be different sizes, and that might make our approximation better as we go too. So something to keep in mind. I know this is some kind of goofy notation. Don't fret over it too much. But with this notation right here, if I can get my mouse to work here and circle that, maybe. There we go. That means the norm of P, which is really just the longest subinterval in the partition. And here's what that question was that I asked earlier. Thinking about this, if that's norm of P, if that subinterval gets smaller and smaller and smaller, the approximation for the area gets better. Now think about why. If the subinterval gets smaller and smaller, what else has to be happening kind of in conjunction with that? Hopefully you're saying, oh, well, then there would be more rectangles. And we talked about that the other day when we went from 10 to 50 to 100 to 500 and how our approximation got better and better and better. We also talked about how that was a limit. And so there's some more notation that goes along with this. And I know that some of you are screaming right now at me, but that's okay. This is just some old school notation, so a little bit of a history lesson here to start with. But this does go back to what we were talking about before. We said the other day that if our subintervals, I guess I should do the P, if our subintervals get smaller and smaller and smaller, meaning getting really close to zero, the limit of adding up all of those rectangles would be our answer. Well, and again, that word adding, here's our summation notation that we talked about the other day. Here is our height, and here is our width that we talked about the other day. So all of that does come back to revisit what we're talking about here. So we're going to use that notation here in a moment. Just a real quick kind of definition idea, I guess. The existence of definite integrals. All functions that are continuous are integrable. Say that 5 times fast. Meaning that we can find the integral of them, meaning that we can find the area under the curve. So let's revisit that notation again. There it is. And that is the definite integral. That's the definition of it right there, using all those pieces. Well, we can simplify this a little bit. And here's how we're going to simplify it a little bit. If I have this interval from A to B, I can figure out the subinterval widths by saying B minus A all over N. Now what's N? N would be the number of subintervals. So if I went from 0 to 4 and I wanted 4 subintervals, I'd take 4 minus 0 and divide by 4. So whatever N is just the number of subintervals. And from there, we can adjust to this notation. So let's think on this for just a moment. Now instead of instead of the norm of p, or the width of the subinterval being approaching 0, here I have n approaching infinity. What would that imply or mean? Well, again, n is how many subintervals. So if the number of subintervals increases to infinity, meaning from 10 to 50 to 100 to 500, what happened to our answer? Well, hopefully you're remembering that our answer got more and more exact. There was this limit that it got closer and closer and closer to what the actual area under the curve was. So that notation is slightly less confusing. Got rid of some k's and got rid of some norm of p goofy language there, notation. One thing to notice, though, is that change of x is in both of these, and change in x is just that width of the subinterval. So keep that in mind, too, as we go. So we're still trucking here. You haven't necessarily had to write anything down yet. Got this notation, but Leibniz, the guy with the big hair, he came up with even some simpler notation. This is the notation that you need to know and love, and we'll see. And here it is, right here, there in yellow. This little squiggly line just indicates the definite integral. The definite integral from a to b, so that's our interval that we had before. We had an interval that looked like this. So that's the a and the b. F of x is just going to be the height of our rectangles. Dx is just going to be that width of the rectangle. So everything's still the same there, still playing the same parts, just slightly simpler notation. We don't have that limit notation anymore, which I think also makes you a little bit happier. The sigma notation, that summation notation, is gone. So we have the definite integral from a to b of f of x dx. All right. So we got that down in yellow there. We're ready to try a couple examples. So we're going pretty speedy here. We're doing pretty well. Let's try an example. You'll have, I think, a problem or two kind of like this today. The interval from -2 to 4, so here's our interval, our a and b, is partitioned into n subintervals of equal length. So to figure that out, where did this 6 come from? Get my mouse to work here. Where'd that 6 come from? Hopefully you're saying, well, b minus a, which is 4 minus a -2, to come up with that, 6. Let m sub k denote the midpoint of the kth subinterval. Express the limit as an integral. Wow, there's a lot going on. Well, this problem is a little less complicated than what it maybe is sounding. And I know that all that notation and the m sub k notation, that looks kind of crazy. But really all that they're doing is they are asking us to take this notation right here and rewrite it in such a way that it says this from the slide before. Okay? So basically, this first part right here is just going to get replaced with the definite integral from a to b. Now what is a and what is b? A and b. The interval, right? So where do I want to start? I want to start at -2 and I want to stop at 4. Then the f of x part here. F of x is really just all this stuff right here in parentheses. But instead of that goofy m sub k is the height of the rectangle, we're going to use just an x. So 3x squared minus 2x plus 5 is going to help us to find that height of the rectangle. And then change in x just gets changed to dx. And that's the end of the story. All right, hanging in there. So you got a couple problems like that. Don't let those directions confuse you. That's all you got to do. Hope you have that one written down because, again, you have a couple problems like that. All right, moving on. Here we go. Got your calculator handy? We're going to need our calculator on the next one. Oops. That was nice. Here we go. Here we got our calculator. An example of using NINT. On our calculators, this is just the notation that our book uses. So when it says find NINT on our calculator, it's this notation. Okay? So to do that, here's what in the end it needs to look like on your calculator screen. Okay? And again, instead of NINT, it's FNINT. And to get there, I believe it is math. And then under that math column, I think it's going to be number 9. I'm checking really quick on my calculator because I forgot to do that before. Yes, it's number 9. And then all the rest of the keystrokes are exactly the same. You're going to type in x sine of x, comma x, comma -1, comma 2. And what all this is, the x sine of x is the function. That was up here. The -1 and the 2 is the bounds up here. And do you remember what the x is? It's the same reason that we put an x in here as we put in deriv when we did that. All that's saying is that x is the variable that we're using in this function. So make sure that you have that in there. And number punch that, hit enter. Hopefully you get 2.04. And hopefully some of you are yelling at me that we should have had 3 decimals there, so that was good. So if you're having some trouble with that, you got to let me know, but otherwise I think that you'll be able to handle that okay. All right, onwards and upwards, here we go. If you need to pause most certainly go ahead and do that. Just hit pause and yell at your calculator for a moment and it'll work. So here we go. Let's go on to the next one. Area under a curve, which is what we were doing when we were doing LRAM, RRAM, MRAM, all of those. We were just finding the area under the curve. We were approximating using some rectangles. And we can do that with the definite integral. The definite integral gives us that exact answer. Remember how when we increased the number of rectangles under the curve that we increased our accuracy in what that area actually was? Well, the definite integral is saying that we want to have an infinite amount of little rectangles under there, and so we're going to make it fit perfectly. And so that's what we're talking about when we talk about the definite integral. Area, this is kind of crazy. We can talk about area being negative. If the area is under the curve, the area is considered to be negative. If the area is above the curve, the area is considered to be positive. To help with this a little bit, and as we progress, then also you make use of this area above minus the area below is the definite integral. What I want you to do, okay, I think I'm resumed. That's good. Just had to get a report on Cammie. She's alive and well, so that's good. Anyhow, where was I at? We got area above minus the area below. And, oh yeah, I want you to turn in your books to page 279 and take a quick peek at Exploration 1. We will actually talk a little bit more about this in class whenever I see you next. But to help with understanding what we have on this slide a little bit, I want you to look at numbers 1 and number 2. And I'm going to tell you that the answer to number 1 is -2. And the answer to number 2 is 0. I want you to ponder that a little bit. I'm going to just talk really briefly. I'm not going to really show anything. I want you to just kind of think on this a little bit. But number 1, as you look at that graph there to the left of it, the shaded area has an area of 2. That's what it tells us. And that area goes from 0 to pi. Well, in question number 1, it asks us to go from pi to 2 pi.